Hello, everyone. Good morning. So it's time to start the morning session of the last day. The first speaker is Shintaro Yanagida from Nagoya. He will tell us about quick introduction to chiral quantization. So please start.
Sorry, sorry, 全然。Let me read that. So, thank you very much for the introduction, and let me thank all the participants and all the speakers so far. I will give some introduction to the so-called chiral quantization, and my talk is mainly a review. And anyway, so this talk is on some quantization. So let me start with the explanation on what I mean by the word quantization. So I use the word quantization as building some quantum systems from classical mechanical systems or classical Hamiltonian systems. So of course, there are many other quantizations that already appeared in this workshop, but I only use the word, I only consider quantization of classical Hamiltonian systems. And this one is, how to say, common notion in physics. And I think this first quantization goes back to Dirac's idea. But anyway, in the finite dimensional classical mechanical systems, a quantization, canonical quantization means replacing the Poisson bracket in the classical system by some commutators in the operator algebra. The so-called second quantization, or in the field theory, there are much more complicated situation. But let me start with a well-known mathematical formulation of this finite dimensional case. This one is called the deformation quantization. For simplicity, let me give an algebraic setting. So a classical Hamiltonian system in algebraic situation can be encoded by a so-called Poisson algebra. So this Poisson algebra is a pair of, or is a commutative algebra A and the commutative multiplication dot equipped with the so-called Poisson bracket. So the definition of Poisson algebra has already appeared in Hayami-san's talk in Wednesday, so I will skip it. But anyway, given such a Poisson algebra, a deformation quantization means a new associative algebra, which is not commutative in general. But anyway, and the base module is the space of formal power series with coefficients in the original algebra. And the new product denoted by star should satisfy the following two conditions. So we have variable h bar. So and in the zeroth order, in terms of h bar, the zeroth order is given by the original commutative product. And the first order is should be compatible with the original Poisson bracket. And this notion was introduced about 50 years ago. And there are many studies of this deformation quantization. And let me mention one of the most important work due to Kosevich. So there is some explicit universal formula of this star product. So this formula can be applied to any or arbitrary Poisson algebra. And let me also mention that this work, or how to say, so such an existence of formula means that for any Poisson algebra, there exists some deformation quantization, and it is related to the so-called Dudolini conjecture, which appeared in Professor Condian's talk. And as I mentioned before, there are many other notions of quantization. One of the well-known notion is the so-called geometric quantization. And this will be mentioned in Chin-Lee-san's talk in this afternoon. So I will skip it. And in the field theory context, there are many other quantization. The well-known one is a Feynman path integral method. And of course, there are much more other notions. So for example, the so-called quantum groups notion, which will appear in Hattori-san's talk in this afternoon. And the so-called Cohn's non-commutative geometry and the so-called Q analogs. And these can be considered as the notions of quantization. But anyway, in this talk, the main notion is a chiral quantization. And this one is a combination of finite dimensional one and infinite dimensional one, or field theoretical one.
Excuse me, a brief question. Is a deformation quantization unique?
No.
No. So the universal formula by Kosevich is just a quantization.
Just a quantization.
Okay, thank you.
So, so let me go to the chiral quantization. But this notion is, anyway. So this chiral quantization is a combination of finite part and infinite part. So it should be complicated. And the definition itself is very complicated. So let me first show a standard example. The standard example, the simplest one, I think, it's still complicated, but let me start. So anyway, I introduce a well-known Poisson algebra, the so-called constant key of Poisson algebra. It can be built from a complex simple Lie algebra G. Given such Lie algebra G, we consider the symmetric algebra of G. So this is a commutative algebra. And we can introduce a Poisson bracket on this commutative symmetric algebra. And this one is the so-called constant key of Poisson bracket. And it is defined for the element in the original Lie algebra G. The bracket of the elements of G is given by the original Lie bracket. And other elements for other elements, the Poisson bracket is determined by this Leibniz rule. So for example, this is the simplest case. So G equals L2. So we have the three-dimensional basis. And the algebra R is a polynomial algebra with generators E and F. And the Poisson bracket is given by the standard Lie bracket relation. So this is a Kirchhoff constant Poisson algebra. And after chiral quantization, we have something. That something is the vertex algebra. And in this case, we have the affine vertex algebra. And affine vertex algebra appeared in Nishinaga-san's talk instead, as far as I remember. But anyway, given the same E algebra G, we consider the affine E algebra G. Then we can construct the so-called vacuum module. So this is an affine, this is a representation of the affine E algebra. And this vacuum module, vacuum representation, has a standard vertex algebra structure, like this. And what is the relation between this affine vertex algebra and the Konstantin-Poisson algebra? So there is a filtration, the so-called refiltration on this vertex algebra, affine vertex algebra, such that considering the associated gradient of this filtration, we can make some Poisson algebra. So using filtration, we can construct from a vertex algebra a certain Poisson algebra. So this Poisson algebra coincides with the Konstantin-Poisson algebra. So there are many undefined notions. So let me explain those. And, so here is the definition of vertex algebras. But this one is already appeared in Nishinaga-san's talk. So I only give explanation on main ingredients. The main ingredient of a vertex algebra is the state space, the space of states, D, and the so-called state field correspondence, Y. So Y is a linear map from the linear space D to the series of endomorphisms or operators. And usually we denote those operators by these symbols. And there are several axioms, but the most important one is the locality axiom. The locality axiom is a little bit complicated, but it is essentially equivalent to the operator product expansion, which was explained by Nishinaga. So anyway, a vertex algebra can be regarded as a linear space D equipped with infinitely many binary operations. This n comes from here. So and the n can be n runs over integers. So anyway, so vertex algebra is a linear space equipped with infinitely many operations. And yeah, so this is a recollection of vertex algebras. And here is a definition of chiral computation, but it's a little bit complicated. So anyway, for arbitrary vertex algebra B, we can construct a filtration, the so-called refiltration, this filtration D. And so the filtration means that the sequence of linear subspaces of the state space V, and each component, each subspace FPV is given by this a little bit strange formula. And it is difficult to read the meaning of this filtration from the formula, but let me focus on the zeroth graded part, which means that the quotient space of the whole space, the whole surface, F0p. F0p is nothing but D itself. And I quote this space by the next step, F1b. And let me denote this quotient space by R. So this RV has a Poisson algebra structure, and it is called the C2 algebra. So the Poisson algebra structure means that we have a commutative product and Poisson bracket. And the commutative product dot is induced by the -1 operation of the vertex algebra structure Y. So recall that. So from the linear map Y, we have infinitely many binary operations. n operations. Using -1 operation, we have a commutative multiplication on this quotient space. Similarly, using 0 operation, we can construct a Poisson bracket. And the resulting algebra, Poisson algebra, is called C2 algebra. And we can, in the algebraic geometry context, we can consider the corresponding affine scheme with Poisson structure. So the Poisson scheme, by considering the spectrum of a commutative algebra RV. And this one is called the associated scheme. And so here is the definition. A chiral quantization of a Poisson algebra R is a vertex algebra V such that the C2 algebra RV is isomorphic to the original R as Poisson algebra. So this is a definition.
Excuse me, who introduced that definition?
No. This one is, I think, originally due to Beilinson and Drinfeld, but this definition first appeared in Arakawa-san's paper. I will.
So you I mean, I'm wondering why it is called chiral.
So chiral means that so the quantization related to chiral algebra. Chiral algebra means Beilinson-Drinfeld.
Great, thank you.
But anyway, in the document or in paper, I think that Arakawa-san first introduced this notion. So anyway, so let me go the first example. And the first example, the affine vertex algebra B. Affine vertex algebra is a chiral quantization of the constant key of Poisson algebra, which is this is the first example. The second example relates W, so the so-called W algebra. And this one is a little bit complicated one. But let me explain briefly. So again, we consider the algebra G, but let me also choose some nilpotent element F. What a nilpotent element means in this condition. And using this G and F, we can construct the so-called slowed-width slice. The slowed-width slice is as a set given by this formula. And restricting the constant key of Poisson structure on this slowed-width slice, so we have the Poisson structure. The resulting algebra or resulting Poisson scheme or Poisson variety is called slowed-width slice. So this is an example for G equals SL2 and F is the standard F. The set SF regular is given by this set of matrices. On the other hand, using G and F and another parameter level K, we can construct a so-called W algebra. A vertex algebra depends on G and F and K. And the definition is too complicated to explain. And here is the most standard one, the most simple one. Choosing G to be SL2 and F is a regular as this one. And K is arbitrary. Then WK is essentially the same with the Virasoro vertex algebra. Also, here the defining relation of Virasoro algebra. But using Virasoro algebra, we can construct a vertex algebra on some representation of Virasoro algebra. So anyway, so I mentioned two examples of chiral quantization. So VK is a affine vertex algebra is a chiral quantization constant key of Poisson algebra, and W algebra is a chiral quantization of slowed-width slice. And these two examples are related in terms of the so-called Hamiltonian reduction. At the classical level, at the Poisson algebra level, the Hamiltonian reduction, I mean the classical one, or in the symplectic geometry terminology. There is some quantum analog or vertex algebra analog of Hamiltonian reduction. And it is, this one is mentioned as a DRS-Dirac reduction or BV formalism in higher distance talk. So anyway, so this is the explanation of quantization and other kind of quantization. And it is natural to ask if there exists or not. And it is in fact exists for any personal algebra, but it's a little bit complicated the situation. But anyway, as far as I understand, this theorem holds. And the outline of the proof divides into two steps. The first step is for any given Poisson algebra R, we construct a Poisson vertex algebra. And the Poisson vertex algebra was Poisson vertex algebra appeared in Hayami-san's talk. And it's a little bit complicated notion, so I will not explain the definition, but roughly speaking, Poisson vertex algebra is a semi-classical limit of vertex algebra. So anyway, we can, for given Poisson algebra R, we can construct an explicit Poisson vertex algebra, so-called level 0 Poisson vertex algebra. So this one is due to Arakawa 10 years ago. The next step is a little bit, the next step is more abstract one. This one is, as far as I understand, abstract resistance theorem. Anyway, for any Poisson vertex algebra, P is there exists a vertex algebra B such that the associated gradient of the refiltration of P gives the original Poisson vertex algebra. So this is due to Tamarkin's theorem on chiral Dorini conjecture. So Dorini conjecture appeared in deformation candidation. But Tamarkin considered about 20 years ago a chiral analog or vertex algebra analog of Dorini's conjecture. And the existence is known by his work. So anyway, such as combining these two construction and existence theorem, we have some existence theorem of chiral quantization. But here is an open problem. As far as I know, there is we don't know an explicit definition and the description of this chiral quantization. So recall that in Kontsevich formula, there is some deformation quantization with explicit formula. But I don't know because this chiral theorem is based on this abstract existence theorem. So we cannot read any explicit description of this vertex algebra. So this is a one open problem. So anyway, this is the I finished the review part of chiral quantization. And in the waste time, and let me explain an application, a little bit, not an application, but anyway, as some related topic, the so-called chiral quantization of Muwa-Tachikawa topological fields. Muwa and Tachikawa introduced and conjectured about 10 years ago a certain functor this form. Let me explain. This target category is the two-dimensional voltism category, VO2. But this is the anyway category. So we have some objects as object is given by the nth product of the oriented group S1. So objects can be identified with natural number n. The morphism between n1 and n2, or n1 product of S1 and n2 product of S1, is given by a two-dimensional oriented, given by a oriented surface with boundary. Its boundary at n1 component, the n2 component is orientation reserved, reversed. And the composition is given by gluing the surfaces. So this picture explains these objects, morphisms, and compositions. This is just the standard one, I think. And Muano-Tachikawa setting, the target category HS is a little bit non-standard. So let me explain. So this category HS is the category of holomorphic symplectic varieties. I denoted quotation marks to mean to stress that this is a little bit non-standard terminology. In the standard terminology in mathematics, the category of something means that the object of the category consists of something. But in this situation, holomorphic symplectic varieties doesn't appear as objects, but appears as morphisms. So the target category HS and the objects are given by semi-simple Lie groups, complex semi-simple Lie groups. And the morphisms G1 to G2 is a certain symplectic variety, a symplectic manifold with some singularity and some nice action of the product of G1 to G2. That's a little bit non-standard setting, but they consider such a setting. But this is a category, so we should have some composition of morphisms. The morphism, so given two symplectic varieties, we can construct some new symplectic variety by using the Hamiltonian reduction or symplectic quotient. So this is a definition of the target category HS. And Muano-Tachikawa conjecture chart that for each simply connected semi-simple Lie group G, there is the functor eta G from the two-voltism category to the category HS with this is the object correspondence. So N or S1 S1 times maps to the product, nth product of the Lie group G. So this is how to say assumption, and they conjecture that there is a family of symplectic varieties with some nice action, the so-called Muano-Tachikawa symplectic variety, such that this eta G is a functor between these two categories. So anyway, a functor from a voltism category to two-dimensional voltism category is called the two-dimensional topological quantum field theory due to Aki and Seeger. So this functor eta G can be called Muano-Tachikawa topological QFT. And on topological QFT, Wakatsuki-san should will explain something in this morning session. So anyway, so we have some topological fields. Muano-Tachikawa conjecture that there is some topological field theory, but the target category setting is a little bit non-standard. And this conjecture was solved by Breberman, Finkelberg, and Nakashima some times ago. And they constructed the Muatachikawa symplectic varieties using the so-called affine Grassmannian and derived category and a little bit complicated convolution product and like that. So anyway, using some high-tech, they constructed some commutative algebra H stuff. And this commutative algebra has some Poisson structure, which is non-degenerate, so it's a symplectic structure. And so then they determine the image of the morphism in some explicit way. And they showed that these families of symplectic varieties satisfy the Goodwin condition. The functorial condition. So it's a little bit too abstract for non-expert, but a few varieties, especially in the genus zero part, can be described explicitly. Let me denote by WNG the image by the functor eta G of the Olympic surface sigma with genus 0 and n connected components. G equals 0 and n equal 2, so the surface looks like a cylinder. Okay, can be considered as a cylinder. And then there is a corresponding symplectic variety of this apparatus. This one is this variety is given by the cotangent boundary of the Lie group G. N equal 1 is a little bit non-trivial, but the picture or surface is given by this drawing. And the corresponding variety is given by the product of the original Lie group G and the Zloroi slice, which I mentioned before. N equals 3 and G is a bit small SL2 or SL3. Then there is some expression and description. So anyways, this is an example of Muatachikawa symplectic varieties. And Arakawa-san considered about 5 years or more before chiral quantization of this Muatachikawa functor or Muatachikawa logical fields. So here I used the word chiral quantization naively, and let me explain the precise meaning. So Arakawa-san considered replacing the target category HS by some chiral number of HS. And he expects that there should exist some functor from the same voltism category to his new category, HSCH. So his category is a chiral analog of Muatachikawa's category HS, and the objects are the same with the original HS. But Arakawa-san replaced morphisms. The original morphisms were symplectic varieties, but he considers that vertex algebras as morphisms. And the composition is given by the BRST reduction or quantum Hamilton reduction. And this new functor, the chiral version should satisfy this commutative diagram. So here, this his new category HSCH. From this new category, considering the C2 algebra or considering associated scheme, so we can construct a functor to the original or old classical target category HS. So we have this functor, and this factor is constructed. And also, Arakawa-san expected the existence of this lift of the functor equation. And Arakawa-san succeeded to build the genus zero part of this chiral version of the functor. So he constructed the expressed family of vertex algebras such that its associated schemes coincide with Watachikawa symbolic varieties. And as a corollary of his construction, Arakawa-san succeeded, Arakawa-san solved affirmatively the so-called beam-steric conjecture with some condition. I will skip this part, but it is related to some functorial construction of vertex algebras from four-dimensional supersymmetric field set. So anyway, by this work, we know that there exists some good functor from Buddhism category, but genus zero part to some category using constructed using vertex algebras. But this one is just a genus zero part, so it is natural to expect to extend Arakawa-san's construction to higher genus case. As far as I understand, this general construction, higher genus version, is not yet fully understood. So anyway, after some thought, it turns out that the target category, CH, should be enlarged. And some years ago, I built such an enlarged target in this paper. So this is the original category built using symbolic varieties, and this one is Arakawa-san's new category, constructed using vertex algebras. But as a target, this one is this one only treats the genus zero part of the chiral version factor. And I constructed a enlargement of this Arakawa-san's category. And I denoted by MTCH. And there would be, I expected that there will be some good functor such that restricting to genus zero, the Arakawa-san's functor is recovered and consistent with Watachikawa functor or Breberman-Finkelberg-Nakajima construction. And I skipped this version, but let me explain what I constructed. Instead of using genuine vertex algebras, I used the complex of the vertex algebras or complex or differential graded vertex algebras as a one morphism. And I constructed a certain infinite category. So this is a higher analog category. And the higher category, such a higher category appeared in several talks in this workshop. And in the higher category setting, we should consider not only one morphisms, but also 2 and 3 and higher morphisms. We can construct such a higher morphisms, but anyway, this one morphism is the essential ingredient. And the composition of the one morphism is given by the quantum Hamilton reduction, but it's certain variation. And I showed that from my new category, taking the derived associated scheme functor. So we have some functor to some derived version of the category HS. The original category, target category HS, there is some derived version, and Arakawa-san's category, and this is my new category. And there are some vertex Poisson version. Poisson version. Poisson vertex algebra appears in higher Nissan's talk, but there are such variation of this construction. But anyway, so all the categories are in some sense consistent. And I expect that, let me repeat that I expect that existence of certain functors eta ch and some eta dr, which are consistent with the already constructed Watachika functors and functor and Arakawa-san's functor. But this is just an expectation, and there are many problems. And one of the most important problem is the description of this DG vertex algebra for higher genus explicitly. And in particular, genus 1 and n equal 1 case is important. And if you succeed to describe it explicitly, then constructing these functors would get easier, I think. But anyway, this is the end of my talk. Thank you for the listening.
Okay, thank you very much for a nice talk and the presentation of your recent work. Are there any questions, comments? How about from the online participants? If you have a question, please unmute your microphone and ask the question. No? Okay, then let me make some general question about chiral quantization. Unfortunately, I can't appreciate the more tactical part, but so about general scheme of chiral quantization. So in the chiral quantization, you don't assume that the Poisson structure is non-degenerate.
Yes.
So how the qualitatively different the chiral quantization if the Poisson structure is degenerate? I understand there, at least classically, there are qualitative difference between degenerate case and non-degenerate case. Then how about how you can see the qualitative difference in the vertex algebra?
So I'm not sure about it would be so in the classical level, the non-degeneracy is a qualitative difference. So general Poisson and symplectic. And in the more Tachikawa setting, so more the category HSL involves only symplectic one, not a general Poisson. And in Brebaman Finkelberg Nakajima construction, only symplectic one appears. And in the Arakawa-san's construction, the Arakawa-san's construction is, of course, consistent with the classical level. So in the vertex algebra level, we cannot distinguish Poisson and symplectic, but after taking the C2 algebra or corresponding Poisson associated scheme, we find that the corresponding Poisson structure is non-degenerate. So at present, I can only say that how to define the symplectic vertex algebra. Then, so one naive definition is yes. So taking the associated scheme or taking C2 Poisson algebra. And if that C2 Poisson algebra is non-degenerate, then let us call such a vertex algebra symplectic. This is a naive definition.
Okay.
But this is not how to say criterion. We don't know. at this moment, I don't know any qualitative criteria for such non-legitimacy.
Okay, okay, thank you very much.
I think maybe it's a good question. Some related work appears recently by Arakawa and Moro's works.
Can I ask a non-scientific question?
Yes, please.
Can you share the slides is it possible to share the slides at some point to to the participants?
Yeah, you can
No,
share.
I mean, can you send the PDF to the chat room or something?
Oh, I'm sorry.
Can you send the PDF file to the audience within the
You mean by chat?
By chat.
yeah, by chat or
the PDF file will eventually be uploaded to our website.
Yes.
Yeah.
okay, that's fine. Okay, that answers my question. Thank you very much.
So it's just to ask to send the PDF file to you. Okay, yeah, actually, we are going to upload most of PDF, a slide of PDF slides on our website. So are there any requests? No,
I have a question.
please.
What are two morphism in your infinity category?
Yeah, from the
Intertwiner or something?
meaning of the some standard technique of constructing higher morphisms from DG categories with some condition. But in my case, the meaning, I'm not sure the meaning to morphisms.
What is a two morphism explicitly? Or
Somehow explicitly constructed by using a simplicial technique. But I'm not sure the meaning of that simplicial construction in this situation.
Oh, you use Khan extension or something? But two morphism is between two vertex algebra, right? That is a kind of intertwine or something by module.
Kind of.
Not me. Thank you. But you use general construction to get the two morphism or three morphism something. You use extension property. Thank you.
So, other questions? So if not, let's thank the speaker again. Thank you very much. So the next speaker is Ansi Bai. So could you share your screen?
Okay. Can you all see my screen?
It takes some. Oh, okay. Yeah, we can see.
Okay, thank you. And
slide.
what if now?
Are you ready?
So can you see my screen now?
Yeah, yeah,
Is that-
yeah.
Okay, okay.
Okay, so the second speaker is Anthony Bai from SUSTEC. It's okay, and
Yeah.
he is about a center of the finite dimensional quantum group. So please start.
Okay, thanks for the introduction, and thank the organizers for putting up this workshop, especially Professor Hayashi for inviting me both to give a talk and to participate in organizing process. I'm going to talk about center of a finite dimensional quantum group. The notion of center is abstracted from the center of an algebra by Lurie. Since then, and even before the abstraction, it plays an important role both in mathematics and physics. In math, there is one solution of the Lens conjecture on Hochschild cohomology, tensor category theory, and other higher representation theory, including what you have seen in Kong's talk or Zhao's talk on Tuesday, that center functors, and closed topological quantum field theory, or TQFT. And it also plays an important role in physics, in boundary bulk relation in topological orders, which says that the suitable algebraic data describing the defects in the bulk of a topological order is always the center of the suitable algebraic data describing the defects on any boundary of that topological order. On the other hand, the study of quantum groups or other quantum algebras, some of them originally arising as deformations of their classical counterpart, have deep applications in various areas in mathematics. Moreover, this field also benefits from physics, for example, through the study of conformal field theory, algebraic quantum field theory, and lattice constructions of topological orders. In this talk, I'll mainly introduce these two notions, center and a special kind of quantum group, which are causa bialgebras. Finally, I will spend a little time announce the result that the two centers of a special kind of causa bialgebras, which are finite dimensional Hopf algebras, coincide with the Drinfeld construction, Drinfeld double construction. Okay, so first I'll talk about centers. We fix a field K, let A be a K algebra. The center of A is defined to be the subalgebra consists of elements which commute with each element of A. It is observed by Lurie that the center can be completely characterized by these two conditions. First is that Z of A is a K algebra, and there is an algebra homomorphism rho from ZA tensoring A to A, such that rho will restricted on the unit of Z, raise identity on A. Second, it is universal, which means that given a K algebra B and an algebra homomorphism lambda, such that lambda restricts on the unit of B, raise identity, then there exists uniquely an algebra homomorphism underlying lambda from B to Z of A, such that the diagram you can think of commutes. This also means that all actions on A factor through Z of A, the action of Z of A on A. So let me first remark that the condition universal would guarantee that if the center of A exists, it exists up to a unique isomorphism. Okay, so the first thing to do is that we check the center satisfy these two properties. First is that Z of A is a K algebra obvious, and rho defined by sending Z and A to Z multiplied with A is an algebra homomorphism. Well, this one is not trivial since we have used, as I show in this equation below, we have used that Z2 is an element in the center of A so that it commutes with A1. Okay, so moreover, this algebra homomorphism rho satisfies the condition that well restricted to the unit of Z, a raised identity. It is also obvious. And we need to check the universal part. Suppose lambda is an algebra homomorphism from BA to A. Then underlying lambda defined by sending B to lambda of B tensoring the unit of A is indeed well defined, as you can check. And also this underlying lambda is an algebra homomorphism. And also you can check that the required diagram indeed commutes, which takes some time, but just believe me. So moreover, this algebra homomorphism satisfying this condition is unique. This concludes our proof that the center of an algebra indeed satisfies these two properties. Are there any questions till now? You can interrupt me at any time. We can formalize this story using the notion of a monoidal category, so that K algebras are generalized to be to objects in the monadic category C, and K-algebra homomorphism is generalized to just morphisms in C, and tensor over K is just tensor product in C. And the distinguished element, one of C or one of B, is nothing but a morphism from the unit object of this monadic category to the respect object. So what is a monadic category? A monadic category is a category C with a binary operation, which I mean functor, from C times C to C, and a zero array operation, which selects a distinguished element I in C, equipped coherent with natural isomorphism as below. And some quick examples. Of course, the category of K-algebras and algebra homomorphism is a monadic category. And let C be a monoid, then C can be viewed as a monadic category with only trivial morphisms, where the tensor product is given by is inherited from the monoid structure. Also, the category R mod H of finite dimensional left modules over a Hopf algebra H is a monadic category. If you are not familiar with Hopf algebra, you can just note that the category rep G of representations over a finite group is a special case, since there is a special Hopf algebra called group algebra. And it is indeed a monadic category, since given two G representations, their tensor product carries a natural G action. Also, as a special case, the category of vector spaces is a monadic category. So since we have a monadic category, we can define the center. And you have essentially seen this definition before, right? Since I have just told you about it in the special case that the monadic category is the category of K-algebras. So the center of it is a triple. Z of it is an object in C, and U of Z and rho of Z are morphisms in C, such that this diagram commutes, and then given any triple, there is a unique. Hi. So, are there any questions?
Some noise. Please mute your microphone.
Okay. Thank you. So if you have any questions, please interrupt me. Okay, so given any triple B, U of B, and lambda satisfying the first condition, there then exists a unique morphism underlying lambdas, rendering the required diagram commutes. So of course, you have seen the first example of K-algebras. And then in the monadic category K of K spaces, the center of V is the space NV equipped with a canonical evaluation map NV to V. NV tensoring V to V. Also, let me remark that suppose the center exists, then we can easily define an action from Z of A tensor Z of A tensor A to A. And it induces a morphism Z of A tensor Z of A to Z of A, making Z of A an algebra in the monadic category. And the action on A is the module action, which is also universal, but I will not go into details to this remark. Okay, so to define center of a Hopf algebra, we need to consider a categorified center. First, a quick recap on two categories. In addition to some data of one category, a two category has two morphisms between one morphisms. Like the case for one morphisms, two morphisms can compose with two morphisms once their domains and the codomains match in a certain way. So the audience previously also asked about two morphisms. Okay, so for example, categories, functors, natural transformations is a two category, and points in a topological space, paths, homotopy between paths is a two category. So the two category center introduces no new conceptual difficulties from one categorical center. This is nothing but, let's say be a monadic two category, and the two center of an object A is nothing but a quadruple. The first three is just the triple, as you have seen before, and there is an invertible two cell eta witnessing the commutativity of this diagram. And also, suppose there are any other quadruple like this, and then there exists one morphism underlying lambda from B to Z of A such that this diagram can think of commutes in a certain way, and such choice of underlying lambda is unique in a certain way. So are there any questions? Okay, so the takeaway message is just the center of A in the monoidal 2 category C box time is still equipped with a universal action Z of A box time A to A. So in the examples of the monoidal 2 category CAT, categories functors the natural transformations under Cartesian product. The center of A is the category and A of endo functors with the canonical evaluation functor. And our main example is that in the 2 category MONCAT of monoidal categories, monoidal functors, and monoidal natural transformations, the center of A is called the Drinfeld center of A, and it is a monoidal category whose set of objects are pairs Z and gamma. Here, Z is an object in A, and gamma is a set of isomorphisms natural in X for consisting of, for each X in A, there is an isomorphism from X tensor Z to Z tensoring X. And the universal action reads Z of A times A to A, sending the pair Z and gamma and A to Z tensoring A. Okay, so this universal action indeed uses gamma, but in a subtle way. Okay, so Drinfeld center appears in both Kong and Zhao's talk, and let us see some examples. First, suppose C is the monoidal category obtained from a monoid. Then the Drinfeld center of C is nothing but the one categorical center of this monoid, of course, with trivial morphisms. And let G be a finite group, then the Drinfeld center of rep G is the category of G graded of G representations. Thirdly, let H be a finite dimensional Hopf algebra. Then the Drinfeld center of L mod H corresponds to the representation category of the Drinfeld double of H. I'll go back to it later. And fourthly, the suitable algebraic data description of the 2+1 dimensional topological order is the Drinfeld center of that of the boundary of 1+1. Of any boundary of this 2+1. Sorry, any 1+1 boundary of this 2+1 topological order. Okay. So a short summary is that we have seen center of an object in the monoidal category. For example, center of K algebra, center of vector space, and we have seen center of an object in the monoidal 2 category. In this case, we can compute the center of a monoidal category itself, viewed as an object in a monoidal 2 category of monoidal categories. Okay, so the second part is center of a Hopf algebra. We will not present the proof of our main result computing the center of finite dimensional Hopf algebras. My aim is to state the result and show why we can expect such a result is true. Before that, I will devote my talk to make the necessary preparation, which are Tanaka-Crane duality and quasi bialgebras. So Tanaka-Crane duality deals with the relation between algebras and its category of left modules. So we send an algebra A to its category of left module. It also sends an algebra homomorphism from A to B to a functor from L mod B to L mod A. Note that the direction is reversed since that the and suppose there are intertwiner from algebra homomorphism phi to psi. Then the component of then it leads to a natural transformation B star from the functor phi star to psi star. So is my interaction still work? It tells me the internet is okay.
Yes.
Okay,
please.
so no. Okay, thank you. Note that on this last level, the action of TK is fully faithful in the sense that all natural transformations B star arise in this way for a unique B in B. Okay, so an intertwiner from phi to psi is an element B in B such that B phi of A equals to psi of A multiplied with B for all A in A. Now let's do an exercise since you have non-TK duality. And this exercise is to equip L mod H for an arbitrary algebra H with a monoidal structure. So suppose we have a functor, so suppose we have a functor L mod H times L mod H to L mod H, then induces an algebra homomorphism delta from H to H tensor. Note that direction is reversed. And suppose we have a functor from L mod K to L mod H, then we will have an algebra homomorphism from H to K. And then in the monoidal category, we have a natural isomorphism displayed as below. Then we will have an invertible intertwiner from between the two algebra homomorphisms from H to the power of 3. Sorry for the typo, and here you can just regard this L mod H tensor blah blah as L mod H. Okay, so summarizing these structures we get on H, we arrive at the definition of a coset bialgebra. A coset bialgebra is an algebra H equipped with the algebra homomorphism delta epsilon and an invertible intertwiner A, which intertwines the two algebra homomorphism from H to the power of 3, subject to some conditions, and I don't assume you see these conditions. Okay, so proposition is that if H is a coset bialgebra, then L mod H is a monoidal category. Then a bialgebra is a coset bialgebra H with trivial A. In particular, H delta epsilon form a co-associative coalgebra. And a Hopf algebra is a bialgebra which admits an antipode, which I do not explain here. So we do know what Hopf algebra is. So let HK be coset bialgebras. Then from a functor L mod H to L mod K, we can similarly extract and data algebra homomorphism from K to H. Sorry, this functor is in the right-hand side. I do not list that there are conditions on such functors that can induce an algebra homomorphism. Okay, so a monoidal structure on F are T2 and T0 satisfying certain relations, which records the compatibility of F with the respective monoidal structure. It will lead to two algebra intertwiners. So it is not hard to understand the following definition. Let HK be coset bialgebras. A coset bialgebra homomorphism H to K is an algebra homomorphism equipped with two intertwiners, and I do not assume either that you've seen these details. Okay, so moreover, suppose F T2 T0 and G S2 S0 are two coset bialgebra homomorphisms. Then we can define a coset bialgebra 2 homomorphism, and so that we have the Tanaka current duality sends coset bialgebra homomorphism to monoidal functors, coset bialgebra 2 homomorphisms to monoidal natural transformations. So are there any questions till now? Then there is a fact. Coset bialgebras, coset bialgebra homomorphisms, coset bialgebra 2 homomorphisms form a 2 category. It is proved in Mac Cruden's some paper implicitly. So moreover, this 2 category denoted by QB is a monoidal category under an evident construction, which are relative tensor product over K. And my main theorem is that finite dimensional Hopf algebras admit center in QB. More precisely, the center of a Hopf algebra H is given by the Drinfeld double of H. So to state this main theorem more thoroughly, we need to state what Drinfeld double is. So let H be a finite dimensional Hopf algebra. Let me remark that its antipode S is an invertible algebra anti-homomorphisms and also an co-algebra anti-homomorphisms satisfying certain relations. And note that the dual space H star has a natural Hopf algebra structure. And we also use HR op to refer to the same Hopf algebra H with multiplication reversed. Now, the Drinfeld double of H is the bialgebra whose underlying vector space along with the underlying coalgebra is this H op star tensoring H, and whose multiplication is given using the data of this antipode. So the fact is that the D of H is a Hopf algebra, and the representation category of D of H is equal to the center of the representation category of H. So now I can restate my, we can revisit my main theorem. So originally there are current duality which sends coset bialgebras, in particular Hopf algebras, to monoidal categories. And we have also introduced in the first half of our talk that given a monoidal category, we can take in center to get those monoidal categories which arise as center of monoidal categories. And for those monoidal categories which arise as center of the monadic category of Hopf algebras, then there is a construction called Drinfeld double. So that Drinfeld double of a Hopf algebra H, when applied to Tangen duality, it arrives the center of the representation category of this Hopf algebra. So my main theorem is just to build this arrow and say that this dashed arrow is also taking center. Sorry. So the main theorem is, so we must say that there is a universal action from DH tensor H to H, right? So it is a concept algebra homomorphism, F T0, T2 and T0, where F is an algebra homomorphism from H to DH tensor H, as we have defined. And it is given by sending H to hat 1 tensoring H1 and H2, and there are T2 and T0. Okay, so I thank Liang Kong and Zhihao Zhang for letting me know centers and the letter for communicating me the Drinfeld center of RepG. And thank you for your attention. Questions and comments are welcome.
Okay, thank you very much for your nice talk. So are there any questions, comments? From online participants, if you have a question, please unmute your microphone and ask the question. So I'm not expert on this area, but I have a very naive question. So your main theorem, please show your main theorem about
okay, there are 2 slides concerning this main theorem.
I mean, is this really useful already? The derivation of the known theorem.
I haven't seen it in the literature, so I think it is a new theorem, but it is understandable given what I have said in my talk. It's like it's understandable through this commutative diagram.
I'm wondering, notion of Hopf algebra and Drinfeld double is, defined.
Drinfeld double is known. A Drinfeld double is constructed in last century, 80s.
These concepts are, defined without referring to the concept of some kind of category.
Sorry, I do not know whether it is defined without reference to category, but it is definitely defined without reference to center of Hopf algebras. Thank you for the question.
Why you need the 2 category to prove this theorem?
Oh, this is a very good question. Since there is a naive 1 category of Hopf algebras or bialgebras, and experts may easily think of that 1 category. However, those 1 category misses some important data, which is needed in the category set, for example, to compute from a monadic category to a Drinfeld center. And as a result, if we compute center in that 1 category, we will not get such delicate structures such as Drinfeld double, which are a quasi-triangular Hopf algebra. We will, if the center exists, and one can show that the center of any bialgebra must be a commutative bialgebra, which is not, which loses some information, I believe.
I see. Okay, thank you.
Thank you.
Hello.
Another question from the Nagoya side.
Hi, I'm Yanagida.
Hi.
Nagoya. Clear talk. And your theorem is a finite dimensional one.
Uh,
You
I
find it?
don't. Yeah. Thank you for the question. I believe that this condition is not essential. However, in finite dimensional case, there is an explicit construction of this center, and I have not checked very carefully the infinite dimensional case, but my impression is that in infinite case, the center still exists, but the expression is expressed by a coend, but it is not explicit, and it is so if any work can improve these things, I mean that to make this expression more explicit, then I think the theory will also be nice.
Oh, thank you for your comment.
Thank you. And maybe let me give a remark that you can see in the construction of dream field double, there is a we have needed this dual space, and in the case of infinite dimensional, this dual space will not be so nice. However, there may be other constructions, but only the dream field double construction will not probably work.
Well, in this point, yeah, there are variations of dream field double. Yeah.
Variation?
Yeah.
You mean?
Instead of using dual, we consider H and another, say, H prime, and some non-degenerate pairing.
Maybe we can.
Yeah.
Yeah.
Formalism.
I don't know details. Sorry, I didn't hear your last. Thank you.
In dimensional case, we do not consider dual space, but another operator H prime and non-degenerate pairing.
Okay. This may be a direction, but I do not know. Thank you.
Hi.
So other questions, comments? So if not, let's thank the speaker again. Thank you very much.
Thank you.
So please wait a few minutes for the last talk. Okay, let's resume the session. The last speaker of the morning session is Shun Wakasugi from Nagoya, and he will tell us about string topology from the viewpoint of algebraic topology. So please start.
Thank you for
Please put on your microphone.
Can you hear me? Okay. Sorry. Thank you for introduction and thanks to the organizers for this opportunity to give a talk here. Okay, so let me start. I think my research interest is somehow different from most of the participants. So I will not explain the details, but I explain introductory things. Well, first of all, I'll introduce mapping spaces. So for given topological spaces A and M, and consider map AM, and it is the mapping space from A to M. So it is a space of all continuous maps from A to M. And map AM is also a topological space. So it is its topology is given by the compact open topology, but its detail is not important here. But it is infinite dimensional space because here we assume the map F is just continuous. So there are many maps F from A to M. So it is an infinite dimensional space. And in algebraic topology, we study the homotopy type of mapping space. And this is one of the fundamental problems in algebraic topology. And here, the homotopy type is, roughly speaking, and the shape of a space. And the main target of this talk is free loop spaces. So for a topological space M, the free loop space on M is the mapping space from S1 to M. And it is denoted by Lm. And here S1 is the unit circle in the complex plane. So Lm is the space of all loops on M. And here, the loop is just a continuous map from S1 to M. So for space M, we can consider any loop, so this one, or maybe self-intersecting loops, or even constant loop. These are also loops in our sense. So this is the field space. And in string topology, we study algebraic structures on the homology of Lm, H star of Lm, this one, under some assumptions on M. And so I think some of you are not familiar with homology, so I explain the idea of homology here. In general, for a topological space X, in our case, we consider the free loop space, but in this page, I only consider the, I just assume topological space, and given natural number n, and we have the nth homology of X, denoted by Hn of X. It is a vector space over any field, which detects n-dimensional holes, roughly speaking, n-dimensional holes on X. So an element alpha in this space can be considered as n-dimensional cycle on M. So here's an example when X is torus. There are three examples of cycles. And here, cycle means n-dimensional cycle means n-dimensional object in M, and which has no boundary. So in this example, here I am considering H1 of torus. So n is equal to 1. So they are one-dimensional cycle. So alpha A, B, and C are loops, so they have no boundary. They are one-dimensional cycle. And in this vector space, this loop C is considered to be 0, trivial one, because C is contractible. We can shrink C to a point in this surface torus. On the other hand, we cannot shrink A and B to a point because here there is a hole, one-dimensional hole here. So we can shrink A to a point. Similarly, there is a one-dimensional hole here, so we cannot shrink B. So H1 of X detects one-dimensional hole. And similarly, we can consider H2 of the torus. And the most typical element in H2 of torus is the torus itself. Torus itself has no boundary, and there is a two-dimensional hole here. I mean, the interior of the torus. So it is a non-trivial element in the H2. So the family of Hn of X reflects the shape of X in the sense of this one. Okay, and this is the homology of the space. And now I explain about the loop product. From now on, N is an n-dimensional manifold. We need to assume oriented, connected, and closed for Poincare duality. And consider the free loop space on that manifold. And Chas and Sullivan define the loop product on the homology of the free loop space. So it is a product on the homology of the free loop space, but it has degree minus m. M is the dimension of the manifold. And so we can describe this product as follows. We can interpret the homology of the free space as follows. So given an element alpha in the homology, n-dimensional nth homology of Lm, and it is n-dimensional cycle on the free loop space. And recall that the free loop space is the space of loops. So n-dimensional cycle on the free loop space is n-dimensional family of loops on M. Or in other words, n-parameter family of loops on M. And this can be defined as this can be explained as a mixture of these two products. The first one is the intersection product. This is a product on the homology of the manifold M. For p-dimensional cycle and q-dimensional cycle, we can consider the intersection of these cycles in somehow geometrical sense. And since the ambient space is m-dimensional manifold, the intersection of p-dimensional cycle and q-dimensional cycle has dimension p plus q minus m. This is the intersection product. And the other product is the contrarian product for the base-drift space. So the base-drift space is also the mapping space from S1 to M, but it is not free, but based. And it means that we fix base points in S1 and M. So fixing some point, fixing a single point in S1 and in M. And this mapping space, so an element in this base mapping space, base space is loop, but preserving base points. So say, if sends a base point in S1 to the base point in M. So an element, all elements in the base loop space share the single base point. So given two elements in the base loop space, we can concatenate two loops. So first goes the first loop, and then goes on the second loop. So we have map on the space in this form. So this continuous map induces a linear map on the homology. And the loop product is a mixture of these products. And next, I explain the construction of the loop product from the original article of Chas and Sullivan. For simplicity, here we consider the Euclidean space of dimension 3, or you may consider this as a local picture of three-dimensional manifold, and consider the loop product in this dimension. So H1 tensor H2 to H1 plus 2 minus 3, and so the ambient space M is three-dimensional, so here is minus 3, so H0 over M. So taking element in H1 alpha and beta in H2, as I mentioned before, an element in H1 is one-dimensional family of loops or one-parameter family of loops. So, this one parameter family is the element alpha, and this two parameter family of loops is beta. So, and these are the loops. These are loops, and alpha and beta are subfamilies. And then we have an element here. By using the loop product, we have an element H0 of Lm. It is defined as this loops. So this is H0 of Lm. So the result must be zero-dimensional family of loops. So finite family of loops. This is the intersection considering the intersection of base points. So here we have the image of base points for the one parameter family, and here is the image of base points for the two parameter family. And we found the concatenation of loops here, but for example, considering this loop and this loop, we cannot concatenate these because their base points are different. But considering this and this, we can concatenate these two, and then form this single loop, but self-intersecting one. And similarly, we can consider the concatenation of this. In this way, we have a finite family of loops here. So we have this element and an element of H0 over M. This is the construction of the loop product from, in the sense of Chas and Sullivan, original one. And there's also another description of the loop product. We can consider this diagram. Here's Lm, and the vertical maps are the variation maps. So take a loop here to its base point here, and base point here. And this is the diagonal map. So an element here is a pair of loops with the same base points, having the same base points. And this is a pullback diagram. And we can define the loop product by this composition. And here, concat star, concat is the concatenation map. So since an element here is a pair of loops with having the same base points, we can concatenate them. And here is just an inclusion in this way, but in the base space, we have intersection product here, and it can be written in this form. So this goes from in the wrong way, opposite way. So it's some kind of wrong way map or Gaussian map, and we can lift this intersection product to, and we can lift along this pullback diagram, and then we have the streak map and wrong way map for the inclusion map, this one. And by composing the streak map and the induced map, we have the loop product. And there are several ways to define the lift. And I have explained only the loop product here, but there are many other operations in string topology on the field space, on the homology of the field space. And Cohen and Godin proved that, and the homology of the field space has the structure of a two-dimensional TKFT, topological quantum field theory. And in Yanagida's talk, it is functor from the category of Bourdisms to some another category, but in an elementary way, it can be described as follows. And there's a loop product, and there's some product, and there's also a co-product, and they correspond to leading this way. The co-product corresponds to this surface, bodies, and this is the identity, and they satisfy many actions. The most important one is the Frobenius identity, written here, and it comes from the fact that these surfaces are the same. And the loop co-product is similarly defined as the loop product by using the intersection product. And this is the final slide, and I talk about only a generalization on Garito. And there's also a string topology on Gorenstein spaces. So Gorenstein space is a generalization of a manifold from the viewpoint of Poincare duality and containing the classifying space. And there is also a generalization, and this one is a generalization on M, but we can also generalize S1 to the k-dimensional sphere. So to define the product on the homology of this space, we can use the same method as the group product, and it was studied by Sullivan and Voronov. But we need to use some different way to define the coproduct on this space. And this is my work, but I do not explain about the detail. But it uses this embedding is a finite codimension in some sense, in the sense of Gorenstein spaces. Okay, I stop here. Thanks for your attention.
Great. Thank you. Sorry. Thank you very much for a very nice review and your presentation of your recent work. So, are there any questions? From online participants? No? So I have a very naive question. What is your motivation to consider higher brain topology?
So there are many operations, and it has a structure of two-dimensional and TKFT, but most of the very unfortunately, most of the operations are trivial. So, for example, if the Bordism has a positive genus, then the operation is 0, very unfortunately. But our motivation is to find interesting algebraic structure on the homology. So we generalize M to other spaces for consider this one, and in very generalized sense, I found non-trivial example of such operation in this case.
So what's like the example? I mean, I'm interested in some concrete example of such brain topology.
Yes, there's a concrete example of M and K, and
so what is M in your case?
Sorry, I forgot it, but a very simple one. Sorry, I forgot the detail, but I guess some kind of Eilenberg-Maclaurin space. So, homotopically very simple one here. So it is not a manifold, but something like classifying space.
Okay, thank you. Okay, there's another question.
Hi, Yanagida in Nagoya. So please give a few comments on this Gorenstein space. Yeah, I'm working on algebra. So, for example, in algebraic geometry, Gorenstein ring or Gorenstein scheme is some nice class of schemes satisfying some duality property. I think,
and definition is this one.
The same one in the algebra.
But here, A is a DG algebra.
Yes.
And for a space M, A is the singular cochain algebra of M.
Yeah, like homotopically.
Yeah.
Homotopically.
Yes.
I see.
And if M is M satisfies the Poincare duality of dimension M, it is a Gorenstein space of dimension n. So this is a
So-
generalization of concave duality.
Not sure, but there is some duality object or duality.
Duality.
So in the algebraic geometry, there is a
Uh-huh.
canonical sheaf or canonical bundle.
Mhm.
In this situation, there is some. No, I'm not sure.
Sorry.
But anyway,
have no idea.
anyway, so and the classifying space
Mhm.
satisfies this condition.
Yeah,
Yes,
and
yes. So-
its dimension is minus of the dimension
I
of G.
Probably your your non-trivial example is something like classifying space.
Yeah, it's something like a classifying space.
I see. Thank you.
Any other questions? So if not, let's thank the speaker again. Thank you very much.
Thank you.
So let's close the morning session, and we will meet again at 2:30 in Japanese time and in 1:30 in China.